Okay, let's go. Number 1. Hanny's voorwerp. In 2007, Hanny van Arkel, a Dutch schoolteacher, was participating in the Galaxy Zoo Citizen Science Project, a web-based initiative organized by Chris Lintott at Oxford University, in which volunteers classified images of galaxies from the Sloan Digital Sky Survey. Van Arkel was working through her assigned image queue when she flagged an object below the galaxy IC 2497 in the constellation Leo Minor. The object was blue-green, large, and irregular. It was not a galaxy. It did not match any classification category in the Galaxy Zoo scheme. She posted it to the project's online forum with a question. Voorwerp is Dutch for object. That is what she called it because she did not know what it was. Hanny's voorwerp is a cloud of ionized gas approximately 65,000 light-years wide, comparable in linear scale to the entire Milky Way disk, located approximately 70,000 light-years below IC 2497. It sits at a distance of approximately 650 million light-years from Earth. The gas is emitting light in the characteristic spectral lines of highly ionized oxygen, producing the blue-green color that made it anomalous in Van Arkel's image queue. Highly ionized oxygen requires a photon source of exceptional intensity to strip the relevant electrons, specifically a quasar-class active galactic nucleus producing ultraviolet and X-ray radiation. William Keel at the University of Alabama and the Galaxy Zoo research team published the initial characterization in monthly notices of the Royal Astronomical Society in 2009. The paper identified IC 2497 as the source of the ionizing radiation. IC 2497 has a supermassive black hole at its center. The problem is that IC 2497's black hole is not currently emitting at quasar-class luminosity. X-ray observations of the galaxy found a nucleus operating at a level approximately 100,000 times fainter than would be required to maintain the ionization state of the voorwerp in real time. The explanation that emerged is called a light echo. IC 2497's black hole was formerly an active quasar, producing radiation at the level required to ionize the voorwerp. At some point in the past, the quasar shut off. The accretion rate onto the black hole dropped precipitously, and the luminosity fell. But the voorwerp is approximately 70,000 light-years from the nucleus of IC 2497. Light from the nucleus takes approximately 70,000 years to reach that distance. The voorwerp is still responding to photons that were emitted approximately 70,000 years ago, before the quasar shut off. The quasar is gone. Its light is still arriving. Subsequent Hubble Space Telescope imaging, published in 2010, identified a region of active star formation inside the voorwerp, apparently triggered by the energy input from the ionizing radiation. New stars were being born in the voorwerp because a quasar that no longer existed was still, from the voorwerp's perspective, shining. The light from that quasar is not yet done traveling. What the voorwerp sees, what it is responding to right now, is a universe as it was 70,000 years ago. IC 2497's black hole shut off. By how much, why, and when with precision are not fully established. Quasars in general are not understood to turn off on timescales as short as the voorwerp's light travel time implies. Whatever IC 2497 was, it is not that now. The cloud that documented its existence is still lit by its absence. The question it raises, how something that large can simply stop, has not been answered. Number 2. The Boots Void. In 1981, Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman, a team affiliated with the Smithsonian Astrophysical Observatory and Carnegie Mellon University, published the results of a deep galaxy redshift survey targeting the constellation Boots. They were mapping the distribution of galaxies at moderate cosmic distances as part of a broader effort to characterize the large-scale structure of the universe. What they found in the direction of Bootes was not a structure. It was the near-total absence of one. The region they identified was roughly spherical and approximately 250 million light-years in diameter. In the standard cosmological framework, the universe organizes matter into filaments, walls, and nodes, with voids between them. Voids are expected in common. Small voids, typically 30 to 60 million light-years across, appear throughout the galaxy distribution. A void 250 million light-years in diameter was not predicted to exist. The standard model of cosmic structure formation, even in its modern form as tested against the largest galaxy surveys ever conducted, consistently produces voids far smaller and far less empty than the Booty's void. The probability of a void of this size and depth forming by the gravitational processes believed to govern structure formation is, in the language of the modeling literature, negligibly small. The interior of the Boots void should, based on its volume and the average density of the universe, contain roughly 2,000 galaxies. Surveys have identified fewer than 60. Those that are present are not distributed through the void's interior. They cluster at its edges, consistent with belonging to the surrounding filamentary structure rather than being interior objects. The center of the Boots void is empty. Greg Aldering, then at the University of Minnesota, noted in the early 1990s that if the Milky Way were positioned at the center of the Boots void, the nearest external galaxy would be far enough away that humanity would not have discovered the existence of other galaxies until the 1960s, rather than the 1920s. The Milky Way is not at the center of the Boots void. Something removed what should have been there, or prevented it from forming, across a region of space larger than most cosmological models are built to accommodate. The merging voids hypothesis proposes that the Boots void represents multiple smaller voids merging over billions of years of cosmic evolution. The problem is that producing a merged void of this size requires progenitor voids that were themselves anomalously large, and the merger timescale, when extended far enough back to explain the current structure, requires initial density conditions inconsistent with the observed uniformity of the cosmic microwave background. The math does not close. In deep radio surveys of the Bootes region, conducted through the late 2010s, structured signal detections from coordinates within the void boundary were noted in the supplementary data products of unrelated survey papers. These detections were described as unresolved, of uncertain origin, and flagged for follow-up. The follow-up publications have not appeared in any peer-reviewed journal accessible through standard literature databases. The detections were noted. They were not pursued, not publicly. What occupies the center of a region 250 million light-years across from which 2,000 galaxies are absent has not been determined. The void is real. Its emptiness has been confirmed by independent surveys using different instruments over 4 decades. The process that produced it has not been identified. Number 3. The Bullet Cluster. In 2006, Douglas Clow at the University of Arizona and colleagues published a paper in the Astrophysical Journal Letters with the title A Direct Empirical Proof of the Existence of Dark Matter. The title was not hyperbolic. The paper presented observations of a merging galaxy cluster system approximately 3,700,000,000 light-years away in the constellation Carina, catalogued as 1E065 7-558. The system is composed of 2 galaxy clusters that passed through each other approximately 150 million years ago at a relative velocity of approximately 3,500 kilometers per second. The smaller cluster, having passed through the larger, left behind a structure in the hot gas distribution that resembles a ballistic projectile. The system has been called the Bullet Cluster since. Clow's team combined 2 datasets. The first was X-ray imaging from NASA's Chandra X-ray Observatory, which maps the distribution of the hot, ionized gas that makes up most of the ordinary visible mass in a galaxy cluster. When the 2 clusters pass through each other, their dark matter halos pass through each other with negligible interaction. Dark matter does not interact electromagnetically and feels only gravity, but the gas clouds of the 2 clusters collided and slowed. The X-ray emission in the Bullet Cluster is concentrated in the region between the 2 clusters, offset from the galaxies themselves. The gas stayed behind when the clusters separated. The second dataset was weak gravitational lensing, the bending of light from background galaxies by the mass of the cluster, which can be measured statistically across thousands of background sources to map where the mass is located independent of what emits light. The mass maps derived from weak lensing did not coincide with the X-ray gas. The mass was concentrated around the galaxies of each subcluster, ahead of the gas, in the direction each cluster was moving. The mass had passed through the collision without slowing. The gas had not. The implication was direct. The majority of the mass in each cluster was not made of ordinary matter. It could not be. Ordinary matter interacts electromagnetically and would have been slowed by the collision along with the gas. The mass that passed through unimpeded consisted of something that interacts only gravitationally. The observation constituted the most direct spatial separation of ordinary matter from the dominant mass component that had been demonstrated to that point in observational astronomy. Several independent analyses followed, using different cluster mergers observed at different stages. The systems Abell 520, Abell 2744, and Max J0025.4 were all analyzed using the same technique. Each showed variations on the same result: mass distributions not coinciding with gas distributions in merging systems. In the case of Abell 520, the result was more complex: a dark matter concentration with reduced galaxy density at its center, which some analyses interpreted as a possible interaction between dark matter components, and which subsequent papers disputed. What Clow and colleagues demonstrated in 2006 is that the bullet cluster contains a component that is more massive than all its stars and gas combined, that feels gravity and exerts it on background light, and that does not slow down during a collision at 3,500 kilometers per second. That component has not been directly detected by any particle physics experiment. Its nature has not been determined. It is there. The lensing confirms it. What it is made of remains the largest open question in physics. Number 4. The Smith Cloud. In 1963, Gail Smith, a graduate student at Leiden University in the Netherlands, was conducting radio observations of neutral hydrogen emission at 21 centimeters wavelength as part of her doctoral research. The 21 centimeter line is emitted by cold hydrogen atoms transitioning between two closely spaced energy states, the primary tool for mapping the distribution and velocity of gas across the Milky Way. What Smith detected, in a region of sky in the constellation Aquila, was a large concentration of hydrogen gas moving at a velocity significantly different from the surrounding galactic disk material. It was not where it should be. It was not moving the way surrounding material moved. She published the detection in 1963. The cloud has been called the Smith Cloud since. The Smith Cloud is approximately 9,800 light-years long and 3,300 light-years wide. Its mass is approximately 1 million solar masses of neutral hydrogen gas. Its current position is roughly 40,000 light-years from Earth, approximately 8,000 light-years below the plane of the Milky Way's disk, below in the sense of on one side of the galactic midplane. It is moving toward the Milky Way at approximately 73 miles per second relative to the galactic standard of rest. At that velocity, on its current trajectory, it will impact the outer disk of the Milky Way in approximately 27 million years. The collision is expected to produce a burst of star formation along the impact region as the infalling gas compresses and exceeds the threshold for gravitational instability. Felix J. Lockman, at the National Radio Astronomy Observatory, and colleagues published detailed mapping of the Smith Cloud in the Astrophysical Journal Letters in 2008, establishing its three-dimensional structure, velocity field, and trajectory with precision. The paper confirmed earlier estimates of the collision timeline and provided the most complete structural picture available. A follow-up analysis using the Green Bank telescope resolved fine-scale structure in the cloud's head and trailing wake. The problem that has not been resolved is the cloud's survival. A pure hydrogen gas cloud of this mass, traveling at this velocity through the galactic halo, should be destroyed by ram pressure stripping and the ionizing radiation field of the Milky Way's hot coronal gas long before reaching this point. The cloud's outer layers are partially ionized, consistent with exposure to radiation. The core is not. Something is protecting the interior from disruption over the timescales involved in its current trajectory. Metallicity measurements of the cloud, published by Andrew Fox at the Space Telescope Science Institute and colleagues in 2016, using ultraviolet spectroscopy from the Hubble Space Telescope, found that the Smith Cloud contains elements heavier than hydrogen at levels consistent with processed stellar material, not pristine extragalactic gas. This indicates the cloud likely originated from within the Milky Way itself, was ejected into the galactic halo by some past energetic event, and is now returning under gravity. The ejection event has not been identified. No known mechanism from the Milky Way's recent history accounts for expelling 1 million solar masses of processed gas into the halo at the required velocity to produce the observed trajectory. The Smith cloud was identified 62 years ago. Its destination is the galactic disk. Where it came from has not been determined. Number 5. Stephan's quintet. In 1877, Edouard Stephan at the Observatoire de Marseille identified a compact grouping of galaxies in the constellation Pegasus and included them in his catalogue of nebulae. The group consists of 5 galaxies in close apparent proximity: NGC 7317, NGC 7318A, NGC 7318b, NGC 7319, and NGC 7320c. 4 of them are at a distance of approximately 290 million light-years, bound to each other gravitationally and interacting. The 5th, NGC 7320, appears in the same field of view but is an unrelated foreground galaxy approximately 40 million light-years away. Stephan could not know this. The distances were not measurable in 1877. The group has carried his name since. The anomalous feature of Stephan's quintet is not its visual appearance, it is what is happening inside it. NGC 7318b, one of the 4 interacting members, is currently falling into the group at approximately 900 kilometers per second relative to the other members. As this galaxy plows through the tenuous intergalactic gas distributed between its companions, it generates a bow shock, a compression wave moving through material that cannot get out of the way fast enough. The resulting shock structure extends approximately 100,000 light-years across the center of the group, perpendicular to the direction of NGC 7318b's motion. It is the largest known intergalactic shock wave that does not involve a supermassive black hole as its primary driver. The temperature of the gas in the shock region, as measured by the XMM Newton X-ray Observatory, reaches tens of millions of degrees. At those temperatures, the gas emits X-rays. Pierre Guillard at the Institut d'Astrophysique Spatiale in Orsay and colleagues published a study in Astronomy and Astrophysics in 2009, reporting an unexpected finding. The same region that was emitting X-rays from superheated plasma was also emitting infrared radiation from warm molecular hydrogen at approximately 2000 Kelvin. These are 2 states of matter that should not coexist in a shock front at any standard physical model's prediction. Molecules at 2000 Kelvin exist in a gas that is also, in the same region, at tens of millions of degrees. The energy balance of the shock does not account for why the molecular gas survives. When the James Webb Space Telescope released its first public images in July 2022, one of the 5 science targets chosen for that announcement was Stephan's quintet. The Webb data provided the most detailed infrared characterization of the shock region to date. The images resolved emission features within the shock front that were previously blended in lower-resolution instruments. The molecular hydrogen emission was confirmed, the carbon monoxide emission lines within the shock were detected, and additional spectral features of warm dust and organic molecules were identified at positions within a structure whose temperature simultaneously measured in the X-ray range. The collision has been ongoing for an estimated tens of millions of years. It is not explosive in the sense of a rapid single event. It is a sustained, slow-motion process at 900 kilometers per second, producing a shock structure visible across a region larger than the Milky Way's disk. NGC 7318b is still moving. The shock is still expanding. The gas it contains should have been stripped of molecules millions of years ago at the temperatures involved. It was not. What is keeping the molecular gas intact within a shock front hot enough to emit X-rays has not been established. Number 6. CFBDSIR J214947 2-04-0308-9. In 2012, Philippe Delorme at the Institut de Planetologie et d'Astrophysique de Grenoble in France and colleagues published a paper in Astronomy and Astrophysics identifying an object approximately 100 light-years from Earth, the constellation Aquarius. The paper presented infrared, photometric, and spectroscopic measurements, placing the object's mass between 4 and 7 Jupiter masses, below the threshold required to ignite deuterium fusion, the process that defines the lower boundary for stellar category objects. The object had no detectable companion star. It was moving through space alone. Its designation, reduced for convenience to CFBDSIR 2149 to 0403, was drawn from the Canada-France Brown Dwarf Survey Catalogue in which it was first identified. The classification of objects in this mass range is contested in the literature. Objects between 1 and 13 Jupiter masses, commonly used as the outer boundary of planetary formation, are categorized variously as giant planets, planetary mass objects, or sub-brown dwarfs depending on their origin. The distinction matters because it implies different formation histories. Planets form in circumstellar disks around stars. Brown dwarfs and substellar objects form from the gravitational collapse of molecular cloud material in the same manner as stars, simply without reaching sufficient mass for sustained nuclear fusion. An object in the planetary mass range that exists without a host star is either a planet that was ejected from its original system by gravitational interaction with other bodies, or a free-floating object that formed from a cloud fragment independently of any star. CFBDSIR 2149 to 0403's formation history has not been definitively established. Delorme and colleagues initially suggested it might be associated with the AB Doradus moving group, a loose association of young stars moving through the solar neighborhood that originated from a common birth cloud. Membership in this group would constrain the object's age to between 50 and 120 million years, which would affect its mass estimate. Subsequent analysis by Jonathan Gagne at the Carnegie Institution for Science and others, published in the Astrophysical Journal in 2015, found the association with AB Doradus to be statistically uncertain. The object's membership status in any moving group remains unresolved. What is established is the object's temperature. Infrared spectroscopy places it between approximately 700 and 800 Kelvin, between approximately 800 and 1000 degrees Fahrenheit. At this temperature, the object's atmosphere is expected to contain methane, water vapor, and possibly silicate cloud decks. It emits most of its radiation in the near-infrared. In visible wavelengths, it would be essentially invisible from Earth. Objects in the 4 to 7 Jupiter mass range, if formed in circumstellar disks, represent the largest planets that standard core accretion models readily produce. Above approximately 10 to 15 Jupiter masses, objects more plausibly form through direct gravitational collapse rather than the accumulation of a solid core. CFBDSIR 2149 to 0403 sits at a mass where neither formation mechanism is clearly favored, with no host star to provide contextual evidence, no disk to examine, and an age that remains uncertain. An object 4 to 7 times the mass of Jupiter wanders through a region of space 100 light-years from Earth, with no star to orbit, a temperature in the range where methane and water clouds form, and a formation history that has not been determined. It has been in the same region of space, moving at the same velocity, for a duration that cannot be specified. No instrument is currently pointed at it on a sustained basis. Number 7. 2 mass J 2 1 2 6 8 1 4 0. In 2016, Niall Deacon at the University of Hertfordshire and colleagues published a paper in the monthly notices of the Royal Astronomical Society identifying a planetary mass object and a distant star as a gravitationally bound pair. The planetary mass object was designated 2 mass J 21268140. The star, catalogued as TYC 94869271, sits approximately 104 light-years from Earth. What separated them was not a number with an obvious meaning until Deacon's team calculated it. The orbital radius was approximately 6,900 astronomical units, roughly 1 trillion kilometers. At that distance, 2 mass J 21268140 takes approximately 900,000 years to complete a single orbit. For comparison, the solar system's outermost confirmed planet, Neptune, orbits the Sun at approximately 30 astronomical units and completes one orbit in 165 years. The entire width of the classical solar system, from Sun to Neptune, would fit inside the distance separating two mass J2126-8140 from its parent star 230 times over. The planet is so far from TYC 94869271 that from its surface, the star would appear as a point of light only slightly brighter than the brightest stars visible from Earth. The planet experiences no seasons, no meaningful tidal interaction, no solar wind of consequence. The mass of two mass J2126-8140 is estimated between 11 and 15 Jupiter masses, placing it near the boundary between a giant planet and a substellar brown dwarf. It was originally identified in the 2-micron all-sky survey as an isolated object, not as a companion to any star. The association with TYC 94869271 was established only when proper motion measurements revealed that both objects were moving through space in the same direction at the same rate, the signature of a gravitationally bound system, however loosely. A planet at 6,900 astronomical units from its star receives negligible radiation from that star. The surface temperature of 2 mass J2126-8140, estimated from infrared photometry, is approximately 825 Kelvin, roughly 1,000 degrees Fahrenheit. This is not warmth from starlight. This is residual heat from its formation, still radiating outward after billions of years. The planet is warm enough to produce detectable infrared emission entirely from energy stored when it was created. In terms of its relationship to the star it nominally orbits, it is functionally alone. Modern humans have existed as a species for approximately 300,000 years. In that time, 2 mass J2126-8140 has completed approximately 1/3 of one orbit. It was in a different region of its enormous trajectory before Homo sapiens existed. It will complete its first orbit, as observed from Earth, long after any current institution or language is recognizable. Whatever properties it has, its atmosphere, its temperature, its composition, it has had them in effective isolation from its parent star for the entirety of its existence. The 900,000-year period is the longest confirmed orbital period for any known planetary mass companion to a star. The object wanders through a volume of space so large that calling it bound to TYC 9486-9271 requires expanding the definition of bound almost to the point of abstraction. It is technically in orbit. In every experiential sense, it is alone, spending the vast majority of its existence in darkness so complete that even its own sun is indistinguishable from any other star in the sky. Number 8. The Taurus molecular cloud. At a distance of approximately 430 light-years in the constellation, Taurus lies one of the closest and most extensively studied regions of active star formation in the Milky Way. It is not visible to the naked eye. It covers roughly 100 square degrees of the sky, an area 300 times the apparent size of the full moon, and contains approximately 200,000 solar masses of cold molecular gas, dust, and complex organic chemistry. It is called the Taurus molecular cloud, or TMC1, when referencing its most chemically active subregion. Stars are forming inside it right now. The cloud has been surveyed in detail since the advent of millimeter and radio astronomy. Studies by Scott Kenyon at the Smithsonian Astrophysical Observatory and Lee Hartman, published across multiple papers through the 1990s and early 2000s, established the demographics of the young stellar population forming within the cloud. At any given point in the Taurus complex, hundreds of stars at various stages of formation are embedded within the dark material. These include Class 0 protostars, objects not yet hot enough to begin nuclear fusion, accreting material from the surrounding gas, and Class 2 T Tauri stars, which have ignited but are still accumulating mass and have not yet settled onto the main sequence of stellar evolution. The entire stellar life cycle, from gravitational collapse to nascent planetary system, is occurring within a structure 430 light-years from Earth. The Spitzer Space Telescope's comprehensive survey of the Taurus complex, published between 2005 and 2009, identified approximately 215 confirmed and candidate young stellar objects embedded within the cloud. Many have circumstellar disks, rotating structures of gas and dust extending hundreds of millions of miles from the central star, in which planetary formation is ongoing. Planets are being built in those disks right now. The process is invisible at optical wavelengths because the surrounding envelope of the molecular cloud absorbs the light. What is more difficult to explain than the stars is the chemistry. In 2018, Brett McGuire at the Massachusetts Institute of Technology and collaborators published a paper in Science reporting the first confirmed detection of benzonitrile, a ringed aromatic molecule, in the TMC1 subregion. The detection was made using the Green Bank telescope in West Virginia. Subsequent papers from the same team identified other polycyclic aromatic hydrocarbons and complex carbon chain molecules in the same cloud. Molecular structures of comparable complexity were not expected to survive in the harsh interstellar environment, where ultraviolet radiation from surrounding stars destroys chemical bonds. The density of the cloud provides shielding that allows these molecules to persist in concentrations high enough for detection. Amino acid precursors, organic nitrogen compounds, and long carbon chains relevant to prebiotic chemistry are present in the molecular cloud that is closest to the solar system. The chemistry is occurring at temperatures near -440 degrees Fahrenheit, in the dark, at densities a trillion times lower than the air in the room where this is being heard. What produces these molecules at that temperature in those conditions, in quantities large enough for radio detection, is not fully understood. 430 light-years away, in a region of sky that appears to contain nothing, stars are being born, planets are being assembled around them, and organic chemistry more complex than anything the solar system produced in its first billion years is already underway. Number 9. Barnard 68. In the southern constellation Ophiuchus, approximately 500 light-years from Earth, there is a region of sky where the stars stop. Not thin out, not fade. Stop. What occupies that region of sky is a cold, nearly perfectly spherical cloud of molecular gas and dust, approximately half a light-year in diameter. It is catalogued as Barnard 68, named for the American astronomer Edward Emerson Barnard, who included it in a 1919 photographic survey of dark regions in the Milky Way. In that survey, Barnard described such objects as holes in the Milky Way. He was describing what they looked like. They are not holes. They are the densest concentrations of cold matter in the local galaxy. Barnard 68 absorbs virtually all electromagnetic radiation that passes through it at optical and near-infrared wavelengths. Stars visible up to its edge disappear completely at its boundary. The transition from star field to complete darkness spans less than the apparent width of the cloud's edge in high-resolution imaging, a fraction of a light-year of real space. At its center, the column density of material is high enough that it would require a visible wavelength source approximately 30 magnitudes brighter than the Sun, roughly 16 trillion times the solar luminosity, to produce a photon detectable on the far side. In 2001, João Alves, Charles Lada, and Elizabeth Lada published a paper in Science characterizing Barnard 68's internal structure using near-infrared photometry of background stars reddened by the cloud's dust. The paper mapped the cloud's density profile with high precision. The data showed that Barnard 68 fits the Bonner-Ebert sphere model, the theoretical description of a self-gravitating isothermal gas cloud that is either in hydrostatic equilibrium or approaching collapse. The fit was described in the paper as essentially perfect. An essentially perfect Bonner-Ebert sphere, the authors noted, is a cloud that sits precisely at the boundary between stability and collapse into a protostar. The interior temperature of Barnard 68 is approximately 10 Kelvin, about -441 degrees Fahrenheit. This is close to the lowest temperature naturally occurring in the observable universe. At this temperature, molecular hydrogen, carbon monoxide, nitrogen compounds, and complex organic molecules freeze onto the surfaces of dust grains. Chemistry slows. Thermal emission effectively ceases. The cloud is dark in the literal sense. It does not emit photons at any wavelength accessible to most instruments. Whether Barnard 68 is currently collapsing has not been definitively established. Velocity measurements of the cloud's internal gas show no strong systematic infall signature. The cloud may be in a prolonged equilibrium that will eventually end in collapse, or it may be a transient structure that will disperse before a star forms. Follow-up observations published through the 2010s found no clear protostellar source at its center. Something precisely at the edge of gravitational collapse sits 500 light-years away in a direction where no stars are visible. It has been in approximately this state for an indeterminate period. It absorbs everything that enters it at visible wavelengths and does not emit. Whether anything is happening at its center has not been confirmed. And the darkness it produces in the sky above Ophiuchus is not a gap. It is matter in a state so compressed and so cold that the distinction between a dark cloud and whatever a dark cloud produces when it finally falls inward is a question of time. Number 10. The Horsehead Nebula. In 1888, Williamina Fleming, at the Harvard College Observatory, was analyzing photographic plates taken through a telescope mounted at the Cape of Good Hope when she noted an indentation in a bright emission region in the constellation Orion. The indentation was dark. The bright background was the emission nebula IC 434, energized by the ultraviolet output of the nearby star Sigma Orionis. What Fleming identified was not an object in the usual sense. It was the silhouette of something that did not emit light, pressed against a curtain of something that did. The dark structure is a protrusion of the Orion molecular cloud complex, catalogued by Edward Emerson Barnard as B33. Its distance from Earth is approximately 1,375 light-years. The silhouette is roughly 2 light-years tall. At optical wavelengths, it is effectively opaque. The material inside it, primarily cold molecular hydrogen, dust grains, and complex carbon compounds, blocks visible photons completely. A camera pointed at it sees nothing where the nebula stands. Infrared telescopes penetrate it. What they reveal inside the structure's apparent darkness is active star formation. The interior of Barnard 33 is collapsing under its own gravity in regions dense enough to initiate nuclear fusion. At several locations within the dark column, protostellar cores are in the process of becoming stars. The Horsehead is not an absence. It is a nursery that blocks its own light. The ionizing radiation from Sigma Orionis is eroding the nebula's outer surface from the outside. The process is called photoionization. The bright rim at the base of the silhouette, visible in high-resolution optical images, is where the radiation meets the edge of the cold gas and heats it to emission. Thomas Haworth at Queen Mary University of London and colleagues modeled the erosion rate in papers published through the 2010s. At the current rate of ablation, the structure as it presently exists will be dissipated in approximately 5 million years. In 2023, the James Webb Space Telescope published high-resolution infrared imaging of the Horsehead's upper edge. The Webb data revealed complex organic molecules in the surface layers, polycyclic aromatic hydrocarbons, carbonyl compounds, and molecular features consistent with the chemical precursors to amino acids. Els Peters, at the University of Western Ontario, led the analysis. The findings were published in Astronomy and Astrophysics. The molecules exist at the boundary between the cold molecular interior and the ionizing radiation from outside, in a transition zone where chemistry of considerable complexity is occurring at temperatures near absolute zero. The Horsehead Nebula appears in more public-facing astronomy photographs than almost any other object in the sky. Its shape is immediately recognizable. It has been reproduced on textbook covers, observatory posters, and the first public images released by the Hubble Space Telescope in 1990. None of those images show what is inside it, because what is inside it cannot be seen at visible wavelengths. Every photograph of the Horsehead Nebula is a photograph of a process that cannot be photographed. Stars are forming inside it right now, 1,375 light-years away, in a region that appears to the human eye as nothing more than a gap in the light. If you want more videos like this one, subscribe and hit the notification bell so you don't miss what comes next. Leave a like and drop a comment below. Let us know where in the world you're watching from.